In the previous lesson, the eutectic diagram that we presented was a relatively simple diagram. We know that if we look at the diagrams that currently exist with respect to binary diagrams, these diagrams have already been determined. However, what I'd like to do is to go back and analyze how we would, in fact, determine what the phase boundaries are, and by doing that, we may get an idea of how more complex phase diagrams could be determined in the future. We'll begin with a simple eutectic, and what we're looking at then are a series of alloys that go across the composition range. And as we did in the isomorphous system, we're going to go through a process of equilibrium cooling. And if we begin with alloy 2, we're going to look at the thermal behavior as we cool through a two-phase field at a constant rate. And of course, what happens is when we reach the liquidus boundary and we continue on through to the solidus boundary, we actually see a change in slope. And that change of slope is occurring because as the temperature is dropped, a small amount of solid material is beginning to form, and as we go further down in temperature, we get more and more solid form. So rather than having a horizontal arrest line, what we're going to see is a change in the slope, and we look at the boundary of the liquidus and we look at the boundary of the solidus, and we see there a discontinuity with respect to the presence of that cooling curve. When we look at alloy number 3, with respect to alloy number 3, what we see is that's a composition that goes right through the eutectic reaction. And we see a change of slope, and that slope change is occurring at the eutectic isotherm. Here we have a horizontal arrest line. The reason that we have that horizontal arrest line is because that eutectic reaction is invariant, and once all of the liquid has transformed to solid, created a heat associated with that solidification process, the actual temperature of the sample is reduced, is retarded, so that once we convert all the liquid to the solid, we now follow the cooling curve that is associated with the cooling rate of the furnace. So that horizontal arrest line occurs exactly as it does when we talk about solidifying that pure substance. Now, when we look at alloy number 4, I want to bring close attention to this because it's made up of two parts. When we come down through the upper temperature range out of the liquid, we reach the liquidus boundary, and as we continue to go down toward the eutectic, we see the change in slope, which is essentially what happens in that two-phase field. Once we reach the eutectic isotherm, any liquid that happens to be left over winds up converting to solid of alpha plus beta from that liquid phase that's remaining. And because it's occurring at a single temperature, we again have that horizontal arrest line. Now, if we want to look at solvus boundaries, and what I have illustrated on this eutectic diagram are a series of points indicating the examination of the microstructure inside and outside of the single-phase field. And when you look outside in the single-phase field, what you're going to see is only one phase present in the microscope. So you spend some detailed amount of time at looking at different compositions and then seeing how many phases are present. Then what can be done is to choose alloys that lie inside of where we predict the phase boundary might be and examine how much of those individual phases do we have and what are the compositions of the phases. So for example, if we choose an alloy that's right in the middle of that two-phase field and we allow it to achieve thermal equilibrium, we're in a region where we have two phases. So what does that mean? Well, what it means is from the micrographs, we can determine how much of alpha we have and how much of beta we have. And in addition to that, we can also determine what the compositions of the phase boundaries are. So as a result of that, we would be able to locate that phase boundary for that isothermal condition. And so consequently, all we would need to do is to go through a series of isothermal holds at different temperatures with that particular alloy, and then we would be able to calculate what the phase boundaries were based upon the compositions that we would actually measure inside of a microscope or a device that had the ability to determine the composition on these relatively small particles that come out as a result of the two-phase structure. And what we have again is the fact that at the boundaries we have the amount of B that is in the alpha phase and the amount of B that's in the beta phase. And again, increasing or decreasing the temperature will move those points, and we can therefore set the boundaries using that single alloy. Now, when we look at a diagram like the eutectic diagram, there's something that I want to point out here, and it ties back into discussions that we had in previous modules. So at this particular point that I've circled, this point indicates the maximum solubility that I have of component B in that phase that I'm going to refer to as alpha. So I have the maximum solid solubility, and that maximum solid solubility will increase as components A and B become more similar, or alternatively, as A and B become more different from one another. What's going to happen is that point is going to move from right to left. So those materials which have large deviations with respect to Hugh Rothery's rules, then what that's telling us is the maximum solid solubility is going to decrease as indicated on the diagram. And ultimately, we can wind up with diagrams in which we have essentially only A and only B in terms of the solids that are being present. However, we should point out that there will always be a small amount of A that dissolves in the liquid phase in that liquid plus A2 phase field, as well as B that is dissolved in the liquid phase in the liquid plus B field. And again, there will be some B that dissolves in pure A below the eutectic temperature, and there will be some A dissolved in B. And the reasons for those small amounts of dissolving of the components in the other phase is simply because of entropy effects. Thank you.